All right, here we go. New chapter. Okay. Chapter 11 is all about areas. Chapter 12 is all about volume. Um, you're going to be lots of formulas. I've never actually counted how many formulas chapter 11, but there's bunches and bunches and bunches of them. All right. Here we go. There's a bunch of postulates, and I think these are actually the last postulates we'll have in the book, but we'll have plenty more theorems. All right, so write this down, book of truth. Actually, make sure this is in your book of truth. You should have this copied down. If you want to write this so it's nice and close to you for this chapter, that's fine if you're rewriting in. We've already defined quadrilateral before. Remember, a quadrilateral is a polygon. A polygon is a figure made up of segments joined at their endpoints, and it's on a flat surface. So we say a closed plane figure made up of segments joined at their endpoints. That's a polygon. And this one's a polygon with four sides, quad, four, lateral sides, four sides. Okay. We've also had the definition of square. Square is quadrilateral with four right angles and four congruent sides. We may have defined it as a rectangle with four congruent sides before, but this is a fine definition as well, too. Okay, and then the last one, this is what the entire chapter is all about, is calculating area. And the basic definition of area is the space enclosed by a plane figure. A plane figure means not unadorned, right? It means two dimensions. So you have a shape that encloses, I'm trying not to use the word area. You have a shape like a square, and the stuff that's inside the square on a plane, that's what we define as area. Right, pretty weak definition either way I described it or what's in the book right here. Space enclosed by a plane figure. Should say by a closed plane figure. I would add that. So we start off our I don't know, exploration into area with talking about squares. So there's this, I'm going to claim that's a square right there. So it's a quadrilateral with four congruent sides. I don't have tick marks there, but I'm just claiming that's a square. It is closed. Closed mean that it's not open. So here's four sides, a little question mark looking thing. But since I can get to the inside, what do you mean I can get to the inside? What I mean is, well, I can get to right here. If I'm right here, I'm inside the shape. If you try to do that with the square over here, you have to cross a black line. So closed means you can't get to the inside without crossing one of the sides. All right, so it's closed, it's flat, so it's on a flat surface, a plane, and it has four right angles. So that's the definition of a square. Postulate 17, remember we don't prove postulates. Postulate states that if you want to calculate the area, how much stuff is inside a square, you take any one of the sides and you square it. That's literally why we say that something to the second power is squared. So that's our first of many formulas. Now, this shouldn't be news to you. It should be something you're all very familiar with. But I do want to, I'm not necessarily proving this to you because it's a postulate. I do want to at least expound upon this idea, try to clarify it a bit better. So here's my clarification. Imagine a small square, and a small square with side length of 1. I don't know what the units are, so I'm just going to say units. So if it's a square, that means all the sides are 1. Now, if I stack a square of unit 1 onto another square of unit 1, and if you look at the overall shape right there, well, that's not a square anymore. I would need to add 2 more of those. So now I have a square made up of 4 squares, all having a dimension of 1 unit as their side measurement. And if you think about it now, this square has a side length of 2 squares, and 2 times 2 is 4, and that's not surprising because there's 4 squares there. If we extend this idea further, now I have a square of length 4, all the sides, and there are 16 squares there. 16 squares of unit 1. And if you haven't already realized this, when we say that something has so many square inches, kilometers, miles, whatever, we literally mean how many tiny squares can you fit inside that shape that have a dimension of 1 unit, whatever that unit may be. If we're talking about square inches, then the squares have a side length of 1 inch. Sorry, I was just sneezing. All right, so this one has a side length of 4. All the sides are 4, and 4 times 4 is 16. So there's 16 little tiny squares that make up the big square. And that's why we call it square units. Postulate 18 says the following. It says that if two shapes are congruent, well, then they must have the same area. Now, why is that true? Once again, I'm not proving it, just expounding upon the idea. Let's see. If two triangles are congruent, that means they're the same shape, triangles. That means all their sides are the same. So that means they would enclose the same amount of space. So for instance, this is just one of many statements I can make. If true triangles are congruent, then it means their areas have to be equal. Hopefully that's obvious. Now you can have equal areas of different shapes. I mean, you could have a triangle that has the same area as a square. Then they wouldn't look the same, but they could enclose the same amount of space. But we wouldn't say that the triangle is congruent to the square. However, if two squares are congruent, then they must have the same area. So that's postulate 18. Boy, we're knocking these out pretty quick. Postulate 19, well, let's see, we started off, postulate 2 was the segment addition postulate. Postulate 4 was the angle addition postulate. Eventually we had the arc addition postulate. I can't tell you which one that one was. And then now we arrive at this one, and this is called the area addition postulate. So the area addition postulate says this: take any shape, I'm taking a pentagon here, break it up into smaller shapes. So I broke it up into 3 triangles. And as long as the triangles do not overlap, if I add up the areas of the 3 triangles, well, then it would equal the entire area of the larger shape. It's postulate, that's kind of like a dull one, right? So this one doesn't officially have a title to it, like angle addition postulate, but we're adding up individual areas of smaller pieces of the larger shape. So maybe area addition postulate, something like that. Keep forgetting you can pause this. All right, new definition or not. So we talked about rectangles before, but remember the definition of rectangles: a quadrilateral with just 4 right angles. Remember, all squares are rectangles, but not all rectangles are squares. So let's see, it's quadrilateral, 4 sides, it's got 4 right angles, 1, 2, 3, 4. And what else about it? Well, way back, I don't know, probably 3rd or 4th grade, you were introduced to this idea of area. And you were given a formula for area of a rectangle, and you were probably told it's something about length and width. And then eventually you got to pre-algebra and they said, oh, forget about the length and width. We're going to talk about base and height. So the base is any side of the rectangle. You can pick any side, left, right, top, bottom. The height is the distance between the base and the opposite side. So I don't know, pick a side. Let's see, I'm going to pick the left side. So if I say that the left side, B for base, little b for base, if the left side is my base, then the perpendicular distance between that base and the opposite side, that red line right there that I just drew, let's see, that would be called the height. Okay, H for height. Okay. Now, typically speaking, I'm going to show you a better picture here in a second. Typically speaking, yes, we generally use the bottom of a rectangle for the base. Doesn't have to be. And generally speaking, the height is always going to be a dotted line, generally speaking, with an arrow pointing to the opposite side. Usually this arrow goes all the way to the top, and then a little tiny H next to it. But check it out. It's a rectangle. So if it's a perpendicular distance, let me do this in blue here. If it's a perpendicular distance, that means any side. Well, there's a right angle right here. So any side could be the height. So in fact, in this particular one, we get rid of the red dotted line, then the height is the right side. Now that only works for some specific shapes, rectangle being one of them. So base and height. Okay. All right. Moving on. So we're going to do a very challenging proof. And I say it's very challenging because it proves a very simple idea that you've been using since, like I said, 3rd or 4th grade, that the area of a rectangle is length times width. And except we're going to say base times height now, but the 2 words, you understand the concepts are the same. But to actually prove this idea, it's pretty challenging, right? So your fourth grade teacher probably, if you did ask the question of why is it length times width or base times height, they probably just said, just do it, right? And when you ask why, the question of why is it length times width. So I'm going to actually prove it. And now you understand why your fourth grade teacher said, it's pretty hard to prove. All right, so here's my rectangle. It has a height of h and a base of b, and I'm going to prove that the area is base times height. This is a pretty complicated proof. All right, so here we go. Step number one, I'm going to extend the side length h. So notice that's the left side. I'm going to extend it b units. So that red dotted line right there, I'm going to claim is b units. I'm going to extend the other side as well, b units. So that means that side is b and now that side is b. Okay. Now let's see, what else could I do? Oh, well, I can enclose the bottom. And since that shape was a rectangle, and since I made B, I just extended line H right there, so I wouldn't have changed any of the angles. So therefore, if I enclose it, that length right there on the bottom that would also be B. So I've made a square. Okay. And that's just a basic construction right there. So could you construct a perpendicular line that connect the 2 points? You absolutely could. Okay. All right. What am I going to do next? Oh, I'm going to do the same thing, but to the right of that black rectangle right there. But I'm going to extend the side, not B units this time, but H units. So I'm going to extend that line B there, H units, and then, well, I'm going to go straight down and do the same thing. Where I see that black line, I'm going to do it again, H units. I'm making another square there, right? And then at the bottom, I'm going to extend it, and then I'm going to connect the lines. So I made a square in the bottom left, I made a square in the upper right, and then lastly, hey, I made a rectangle, right? That would be HB. Hey, you would have the same dimensions. Let me diagram this one for you. That would be the same. This rectangle right here would be the same rectangle as this one right here. Look, they both have the side length of B and H, so they would be exactly the same. They would be equal. Okay. Right here, let's see. I got a square length of B and B, and over here I've got a square length of H and H. Okay. All right, so here's what I'm going to state. Since I have two rectangles of the same dimensions, right, I could say that those two rectangles, the black one and the lower right one, are exactly the same. I'm going to say that their areas, they're a number. I'm going to assign that number the value A. So that one has an area of A, and this one has a area of A. So you can see which one I'm putting the A's on. So because they're a rectangle of the same dimensions, by postulate 18, it says any congruent shapes have equal areas. I'm just going to claim that the area is A. It's a number. Okay, what about the squares? Well, they're clearly not the same size, but what could I say? Well, let's take a step back and let's look at what we've made. I've made a huge square, right? Look at this. If we look at the entire shape, I got to do this in different color. Let's pick green. I've made this side, this side, this side, and this side. And check it out. Each side is a B and an H. Each side is a B and an H. I didn't label this B, but I could. I didn't label this side as H, but I could. That's a horrible H. Each side is a B and an H. So all four sides are exactly the same. And since all corners are 90 degrees, the big shape is a square. So I can make this statement right here. The area of the big square would be a side measurement. The side measurement would be H plus B. Let's see, I'm looking at that first postulate 17, that stated that the area of a square is a side squared. Well, side is H plus B squared, right? That's postulate 17. There's another way that I could describe the big square. So there's a weird way of describing it. There's another way. I could say that since the two rectangles were size, their areas was size A, and since I have two of them, that I could say 2A plus the bottom left square. The bottom left square has a side length of B, so that would be B squared. And then the upper right one is side length of H, and it would be H squared. So now I can write two different ways of the same measurement. In other words, the area of the big one could be written as the quantity h plus b squared. It also could be written as 2a plus 2a plus h squared plus b squared. Well, if you have two things, and this is postulate 17 and 19 I'm combining, well, I have two statements there where they both say area of the big, so therefore by substitution, I could set them equal to each other, and that's what I did. Now, the next step is a side note. Let's see, I need to do some math here. I need to do square. So remember, when you square a binomial, that's two of those, so that's h plus b times h plus b, and you know me, I like to stack these when I multiply. Unfortunately, the answer is not h squared plus b squared. That's called the freshman's dream. Doesn't work out that way. Watch what happens when we do the math. Just the normal algorithm for multiplying a binomial times a binomial. You probably like distributive property. I like stacking. Let's see, b times b is b squared. B times h is bh, or hb. And everything would be positive. Drop down. H times b is another bh. And h times h is h squared. I like doing the stacking method when I multiply binomials. Draw a line and add. Let's see, that would be h squared. It looks like an n squared, but it's h. Plus 2bh. A bh plus a bh is 2bh. Plus b squared. So that is what circled there in red turns into. So I'll erase all that here in a second, but turns into h squared plus 2bh plus b squared. Now I'm going to erase everything. Okay. So that's just some algebra, some, multiplying binomials. Now look at the left side, look at the right side of that ugly equation. Both sides, right? Can you see it? Both sides have an h squared, so that would go away through subtraction. Both sides have a b squared. Well, that would go away by subtraction. So we would simply be left with 2bh is equal to 2a. Well, since I have a 2 on both sides, I could divide both sides by a 2, and I would be left with bh is equal to a, or a is equal to bh, and that was what we were trying to prove. So I did it, right? Just a little bit of division, and we get to that. Now, what were we doing? Well, we were trying to prove that the area of a rectangle is base times height. Now, as you look at this proof, pretty complicated, easy to follow when you see this. But boy, this is why we don't show it to fourth graders, right? They can't do a binomial, square a binomial. And they don't even know what canceling from both sides or doing any algebra is in fourth grade. So this is why your fourth grade teacher simply said, hey, trust me, it's base times height or length times width. All right. So second formula, first one was rectangle. I'm sorry, first one was square. Now we got to rectangle. So a rectangle, the formula for it is base times height. And you're like, well, can I go with length times width? You can. Nothing wrong with that. I just want you to remember that both the length and the width and the base and the height could be any one of the sides of the rectangle itself. Usually for the rectangle, we don't use a red dotted line for the height, but you could. Usually we use one of the sides for the height. Okay, quick note, just remember that when you're calculating the area, the answer must always have units, and since it's area, the units will be squared. So square centimeters, squared miles. And remember, this also can be read two different ways. You can say the word centimeter squared or squared centimeters, and it means the same thing. When you write it, however, that's the only way you're going to write it. So cm to the second power. All right. When there are no units, you just simply put units squared. All right, we're almost to the end here. Why is there a line right there? Oh, I know, there's shading involved. I got to fix that on my PowerPoint slide. All right, imagine that little blue line there is not there. Okay, so I got a weird shape. How do we calculate the area of this shape? Most kids intuitively immediately reach for the answer. If you don't see the answer, well, we don't have a formula for this. I don't know what you would call this, a sideways L or something like that. But most kids intuitively see, hey, look, I can break this up into two rectangles. There's two ways of doing it. I can either draw that line or a vertical line, but either way, I break it up into two recognizable rectangles. The only issue is this, I don't have all the dimensions. So I got a big rectangle and a small rectangle, right? So the area of the weird shape is going to be equal to the area of the big rectangle plus the area of the small rectangle. That's postulate 19. So let's see, what's the big rectangle? Well, it has a side length of, well, it has a top of 8, but I don't have the side length. This number 5 right here, this number right here, 5, is from here all the way to the bottom, but I don't need that. I need it from here to here. Well, if the whole thing is 5 and this piece is 2, well, then that would leave 3 for the side. I probably have a 3 here. Do I? Yeah, I do. All right, let me clear all that stuff out. So therefore, the big rectangle would be 8 times 3, in other words, 24. What about the small rectangle? Well, the small rectangle is a bit more straightforward. The small rectangle has, this is 6 and this is 2. 6 times 2 is 12. So if we put all that together, 8 times 3 is the big rectangle, 24. The small one is 6 times 2, 12. 24 plus 12 is 36. And remember, we have to have units, so 36 square units. Okay? And that would work whether or not we drew the line there or we drew it straight up and down like that, right? We would get the same answer. All right, we'll do this one for grins. Let's see, it's still going to be big rectangle plus small rectangle. So let's see, the big rectangle would be a 5 and a 6. So let's see, 5 times 6 is 30. We'll do the units at the end. And the smaller rectangle, well, if this is 8 and the bottom is 6, then that leaves 2 for here. And if this side is 5 and this side is 2, then that leaves 3 for here. And 3 times 2 is 6. And guess what? We still get 36 square units, 30 plus 6. Now, some smarty pants out there can probably figure out a third and final way of doing this. And that is, well, imagine that white space there wasn't there. We would have a larger rectangle. So if I extended that line and that line, we would have a larger rectangle. And I can calculate the area of that larger rectangle. In fact, it's pretty easily done. It has a side, the larger rectangle has a side length or base of 10 and a height of 5, which would be 50. So if I knew that, I would simply need to subtract the smaller rectangle, the white one there. And let's see, it has a dimension of, 10 minus 6 is 4. So it would have a dimension of the bottom here of 4, right? I probably have a 4 next. I do. All right. So 2 times 4 is 8. So that would be what? 50 minus 8? By the way, this is a different numbers than the previous one, right? So that would be 50 minus 8, which would be 42. So we weren't getting to 36 because I wrote different numbers. All right, just to prove to you. So let's see. We have 10 as the top. So what did we have on the previous one? We had an 8. So now I just made it into a 10. Okay. Makes sense? Okay. So homework tonight will look more like this than it will look like the previous ones. All right. So if you get to the table thing right here, as always, everyone freaks out over the table. And it's always not the first couple ones. It's always kind of like the last couple ones. Like, like maybe this one, and then maybe one like here, and then maybe one like here. So I'll do all 3 of these real quick. So let's see, number 9, we got the area of a rectangle is equal to base times height. And this time we are actually told the area. So this is just a simple algebra problem. So if the area is 55 and the height is 5, the only thing we're missing is the base. Divide both sides by 5, and we get b is equal to 11. And since this is not area, it would be 11. We got units? Yeah, we get centimeters. So 11 centimeters. All right, so that would be number 9. How about number 11? Weird numbers, right? But it's okay. Let's see, area. I shouldn't erase that. Area is equal to base times height. This time we don't have the area, but we do have the base and the height. There's square roots. It's okay. The base is 4 root 2. Actually, you know what? I'm going to do... No, okay, I'll do this one. 4 root 2 times... And I'm going to write it in a different color, suspiciously. times the height here, and the height is root 2. We haven't done multiplication with square roots in a while, so let's see. The rule is the outside number with the outside number, multiplication. So I need to multiply 4 times the outside number here, which is not listed. But if it was listed, let's see, we would say that that outside number was 1. So answer in red. So 4 times 1 is 4. And then we need to multiply the inside number with the inside number and keep the square root. So inside number with inside number. So 2 times 2 is 4. So we would get the square root of 4. But wait a minute, I know the square root of 4. The square root of 4 is 2. So that would be 4 times 2, which is 8. And were we doing area? We were. So, and this is, there's no units listed. So I'm going to put U for units, units squared. Okay. Probably should write out the word unit though. All right. Let's see if I can erase the right things this time. All right. Last one, number 13. Oh, looks challenging, but it ain't bad at all. I'm not giving the error, but I'm giving the base. So the base is x plus 3. And I'm supposed to multiply that by the height. Well, the height is another letter, so I need to put this in parentheses and multiply it by x. So an unsatisfying answer, distributive property, it would be x squared. So the area would be x squared plus 3x. A decidedly unfriendly answer. And then we would have to put the words units squared. So u squared, I'm going to write the word like I'm supposed to. Units. U squared would leave you the impression that it's u squared instead of the word units squared. And there we go. So that'll do it for today. Good luck on your homework. And as always, if you're running a problem, you know what to do. Okay. And we'll stop it right there.